Well, I hope you're all buckled in because we've got some really wild stuff to talk about. We're going to continue our discussion of exponential functions, and our main theme tonight is going to be looking at annual growth rates. And so our big attempt tonight is we're going to try to model some real-life applications tonight with these functions, whether we're studying the population of a city, or maybe we're studying the investments in your portfolio and how much money you've hopefully gained in the stock market. We're going to try to model that with some exponential functions. And just to kind of set the table, we've got a real nice picture of an exponential function. You see it kind of starts off increasing at a very slow rate, but then that rate of increase starts to pick up, and not only is the function itself increasing, but the rate of change is increasing as well. And so we say this function is increasing at an increasing rate. But what is the difference between an exponential function versus a linear function? And let's try to settle that right now. First of all, a linear function is one that has what we call a constant additive effect. Okay, it's a constant additive. In other words, you're continuously adding by the same amount over and over. Constant additive effect. Whereas, by contrast, when we talk about an exponential function, it has what we call a constant multiplier effect. In other words, you are continuously multiplying by the same value over and over again. If we look at a table of values, and sometimes this paints a clearer picture, first of all, a linear function, as the x values increase by 1 unit, maybe the y values go up by additives of 2. So you notice the y values kept adding 2. By contrast, with an exponential function, if we looked at the same x values, what's going to happen is this time, oops, that would be a 4, and then this will be an 8. What you'll notice here is we are multiplying, in this case, by 2 every time, whereas over here we were adding by 2 every time. Real quick recap of a few things we've talked about already. Our general form of an exponential function looks like this, and we said that a represents the initial value of a function at t equals 0. I'll put that in parentheses. And b is what we call the growth factor. Okay, and basically we'll say it's growing if b is greater than 1, or it could be called the decaying factor. And that would be true if 0 was less than b, which is less than 1. So that's a big decision we'll have to make, is whether the b is greater than 1 or less than 1. So specifically with respect to exponential growth, we're going to say 1 plus r raised to the x. So we're kind of replacing the b with 1 plus r. Whereas when we start talking about decay, we're thinking that it's going to be 1 minus r, where r represents the rate at which the function or population is decreasing. And in this case, we're saying b is equal to 1 minus r. So here, to kickstart things, we've got a function that represents the population of a particular U.S. city, and we want to try to identify these 4 pieces of information just by looking at the equation. And first things first, the initial value is simply going to be the a value. So we'd say this rascal right here is the value of a. So 1,250 people is the initial population. Are we growing or decaying? Well, I'm looking at this b value right here, and I'm going to say, well, this bear is growing because b is greater than 1. Now, here's the more interesting question tonight. At what rate is the population growing? So remember on the last slide where we said b is equal to 1 plus r when we're growing? Well, in other words, we'll say 1.07 equals 1 plus r, subtract 1 from both sides, and 0.07 equals r. Now, a lot of times we're just assuming that we're going to express this as a percentage, so I'm going to move the decimal twice, and I'm going to say we're growing at a rate of 7%. Now, how often? This goes back to the conversation we had about a week ago when we first introduced exponential functions, and you want to zoom in on this value right here. Whatever t is being divided by. I don't know if you remember, we talked about there's a tank filling up with water. Initially had 1 centimeter in it, and it was maybe the height was doubling every 30 seconds or whatever the case might be. That was the first time we introduced that idea. So we'd say every 3 years the population is going to grow at a rate of 7%. Okay, a little more practice with the same style of problem. We've got a function that represents the population of a city. Here's the value of a, so right off the bat, that's my initial value. So this city had an initial population of 350,000. Now this population is decreasing or decaying, however you want to say it, because the b value was less than 1. And that's this rascal right here. That's our b value. Now, as far as at what rate is it decreasing at, well, remember how we defined b as 1 minus r when we were decaying? So I'm going to substitute 0.95 for b. And a couple of things we could do here. I'm going to subtract 1 from both sides, I guess, and that's going to give me negative 0.05 equals negative r. And then I'm going to divide both sides by a negative 1. And that's going to give me positive 0.05 equals r. We're going to move the decimal place twice, and we're going to say it's decreasing at a rate of 5%. How often? Every 6 years, the population is going to drop 5%. All right, one more. I think this is a really good one to try on your own. See if you can answer all 4 of these questions without me saying anything or helping. Now, if I was solving this question, I'm thinking right here is my value of A. So the initial population was 127,350 people. I think my B value is bigger than 1, so we're growing. And that's just because simply my justification is B is greater than 1. Now the rate, so I'm thinking 1.285 is equal to 1 plus r. Subtract 1 from both sides. And I got 0.285 equals the rate. Move that decimal place twice. So 28.5% every 10 years. So that population's increasing 28.5%. Oh my gosh, almost forgot my percent sign. Every 10 years. Just while I'm thinking of it, double check on the last 2 examples and just make sure that I included my percent sign on those other rate questions. Now, how about this? Could we turn it around and they're asking me to write an exponential equation that models a city that has a population of 28,000 and it happens to be growing at a rate of 13% every 5 years. So let's kickstart things here with the easiest part, and that's we know the value of A is 28,000. And then we've got our base raised to, and I think the next easiest thing is to say t divided by 5 because that's how often it grows every 5 years. Now the kicker is, what do I put here for b? Well, I know in this case, since we're growing, b again is equal to 1 plus r. And so I'm thinking that b is going to be 1 plus 0.13. Again, in this case, I can move the decimal back to the left, and that means b is 1.13, and that's all I have to do. Again, very similar to the last example. The only big change is that this population is decreasing. Go ahead and try this one on your own. See if you can come up with the same equation that I come up with. Let's see. My initial population was 152,000, and it's decreasing 8% every 12 years, so I got t divided by 12 as my exponent. Now off to the side, I'm thinking in this case my base is going to be 1 minus r because we're decreasing. So the base is going to be 1 minus 0.08. So remember that decimal sitting right here, we got to move it twice every time. So I had 0.92 as my base, and that's the equation, and that's all I got to do. Okay, just a real quick review of some basic exponent properties, and we want to try to simplify x squared being raised to the 6th power. Typically what we're going to do is we're going to say, okay, let's take this quantity right here and repeat it 6 times because exponents simply represent repeated multiplication. So I'm thinking x squared times x squared times x squared. And this idea of writing it out is sometimes a pain in the butt, but I tell you what, if your chief concern is getting the right answer, then by golly, I think it's the best way to go. Now, if I multiply all these x squareds together, 2 plus 2 plus 2 plus 2 plus 2 plus 2 is going to give me x to the 12th. Now, in hindsight, the shortcut was to simply multiply the 2 and the 6 to come up with the 12, and that's the shortcut I'm going to use in the future here. So in this case, I'm thinking I want to multiply these exponents right here. In other words, I see a power raised to a power, or an exponent raised to an exponent. And what I'm visualizing is 5t being divided by 1, and I'm going to multiply the numerator times the numerator, and then the denominator times the denominator. And that's going to give me x raised to the 5t divided by 3. And this last one, again, I'm going to stress to myself as I'm talking myself through it that I want to multiply these exponents. And in this case, I got x raised to the 10t divided by 10, which simplifies simply to x to the t power because the 10's divide out to a 1. Now here's the first real big kicker of the night, and notice there's certainly, we didn't put stars around this bear for nothing. Nothing that we've done tonight has had to do with annual rate of growth. All of the percentages that we've dealt with so far were every 2 years or every 6 years or every 10 years or whatever the case might be, but nothing had to do with annual, and that was tonight's title. So from this point forward, we're going to be focused on one and one thing only, and that is the annual growth rate or the annual decaying rate. And in this case, we're going to say in order to identify the annual rate of change, the coefficient of t must be a 1. Okay, that's what we want to stress. And of course, annual means every year. Okay, every single year, or in intervals of 1 year. And so that we're going to focus and we're going to keep telling ourselves from this point forward that the coefficient of t must be a 1 before we can identify the annual rate of change. So now in front of us, we've got our first really challenging problem of the night. And here's a function that represents the population of a particular city, and they want me to identify the annual rate of change. So here's the problem. Right now I'm looking at this equation and I'm saying, well, this value is bigger than 1, so the population's growing. And I would say specifically it's growing at a rate of 6% every 2 years. That's the problem. It's every 2 years, but I want to know how fast is it growing each single year. And unfortunately, it's not as simple as just dividing 6% by 2, as we're about to find out. And what the key is we have to manipulate this exponent. And we want the coefficient to be a 1. What is the coefficient right now? Well, right now, the coefficient, and we'll make a note of this here, the coefficient right now is 1/2, because that's what's multiplying the value of t. And so I want to manipulate this equation and force the exponent to be a 1. And here's how I'm going to do that. So the function p of t is really just 1500 times 1.06. I'm going to try to take the smallest steps possible. Right now, I could rewrite the exponent as 1/2 times t, right? Is that equivalent to saying t divided by 2? Well, of course it is. Now, what I'm going to do is I'm going to basically undo this exponent property that we practiced on the previous slides, where I'm going to say 1.06 raised to the 1/2 raised to the t power. You remember how in the last slide we were stressing that we were going to multiply, let's see if we're going to try to multiply these exponents right here. And so I just kind of working backwards compared to what I normally do. And now what I'm going to do is I'm going to type 1.06 raised to the 1/2 power into my calculator, and I'm going to get a fairly feisty number. Notice this outside number, the value of a, never changes throughout the entire problem. 1.02956 raised to the t. Okay, so now here's the most beautiful thing. The coefficient of t is a 1, okay? And I'm going to put a little smiley face right there because we're excited about that, because now we can identify the annual rate of increase. And so I'm going to focus on this number right here. Remember earlier we said b is 1 plus r. So I know that 1.02956 is equal to 1 plus r. And subtract the 1 from both sides. 0.02956 is my r value, or my growth factor. Move the decimal place twice, and I can say 2.956% is the annual growth rate for this particular population. Emphasis on what? Yeah, you got it, the word annual. So my assumption is that last problem was a bear and a half, and you're probably wondering what the heck just happened in the past 2 minutes. Well, good news, we're going to tap the brakes. We're going to practice virtually the same thing, and we're going to try to identify the annual rate of change, or the annual growth rate. See, the problem is right now, I'd say that this population is growing at a rate of 28% every 5 years. And that's not good enough. I want to know at what rate is it growing every single year on an annual, yearly basis. And so my goal is to rewrite this function so that this this coefficient is simply a 1 instead of a 1/5. And I'm going to try to take baby steps once again and see if you trust me, hopefully each step of the way. 1.28 raised to the 1/5 times t power, okay? Remember, t divided by 5 is the same thing as 1/5 times t. And let's see, I'm going to undo that one exponent rule. I'm thinking 1.28 raised to the 1/5 raised to the t, and then I'm going to use my calculator. And when I raised 1.28 raised to the 1/5 power, I got 1.05061 raised to the t. And again, let's emphasize this. This coefficient right now is a 1, and that is worth celebrating. And so I'm thinking 1.05061 is equivalent to 1 plus r. Subtract 1 from both sides, and 0.05061 is my rate of growth. And I want to express that as a percentage, and slide that bar twice. 5.061% is my annual growth rate. Emphasis once again on the fact that it's annual. Certainly, I'd invite you to be my guest and try to solve this one entirely on your own. And then as you finish it, you can come on back and hit play and see if we did it the same way and got the same result. And nothing's going to change from the last two slides. My approach is going to be exactly the same. And I'm going to try to stress that t being divided by 15 is the same thing as saying 1/15 multiplied by t. And that's the same thing as saying 1.42 raised to the 1/15th power, which is all raised to the t power. Best news in the world right here is that the coefficient is a 1. Therefore, I'm just going to try to evaluate this rascal on my calculator. And what does the calculator say? 1.02365 raised to the t. And so I'm thinking, and you could probably do this already in your head, you're looking at this number and you're already subtracting 1 from it, and then you're moving the decimal place twice, and so you're already thinking 2.365% is my annual growth rate for this particular population. Well, we've got ourselves a real big bear now. And this is really going to take everything that we've learned tonight. We've got a population of 28,000 growing at a rate of 16% every 10 years. So this is not our annual growth rate. And they want to know what's the percent growth over a 3-year time period. And here's the kicker, and the number one thing I need you to stress here tonight is that we're going to write our equation, but we're going to then convert it to an annual basis first, okay? In other words, so we're going to go from a 10-year period, convert that to a annual basis, and then we can convert that to a 3-year period. Unfortunately, we cannot go straight from 10 to 3. At least we're not going to try that tonight anyway. So we're going to start off by saying that my population is 28,000, okay? And I'm thinking 1.16 raised to the t divided by 10 power. You're wondering, where did 1.16 come from? Well, that was me taking my percentage, moving the decimal place twice, and then adding that value to 1. So I'm going to convert that. Whoops, going to grab my pen. There we go. I'm going to convert that to an annual basis. And this pesky little 28,000 is just going to tag along. Nothing too exciting. I'm going to skip one step here, if you'll allow me to. It's 1.16 raised to the 1/10 raised to the t, and I'm going to grab my calculator. And as I typed in 1.16 raised to the 1/10 power, I got 1.01495 raised to the t. And so here's my annual rate of growth. It'd be about 1.495% annually. Now the kicker is, I want to get this into a 3-year period. So really what I want to see right here is I want to see t divided by 3 right here. How about that? Think we can pull this off? How could I rewrite this so it's t divided by 3? Well, we're about to get real sneaky. So right now, this is a 1, right? That's an invisible 1. 1.0145 or 1495 raised to the first power. So check this out. Now, just to save a little bit of time, I'm going to kind of skip writing the 28,000. 1.01495 raised to the 3 times 1/3 raised to the t. Now here's the kicker. Do you agree that 3 times 1/3 is equivalent to this 1 I had up there? Of course it is. 3 times 1/3 is 1. Now what I'm going to do is I'm going to pull this rascal out here. And that's going to give me exactly what I want to see on the outside. 1.01495 raised to the 3rd raised to the t divided by 3. Now what I'm going to do is I'm going to grab my calculator and I'm going to type this part into my calculator to get my new base value. And let's see, my calculator says 1.04552. and that's raised to the t divided by 3. And so I can say on an every 3-year basis, we're increasing 4.552% every 3 years. Okay? So the key is we couldn't jump from 10 to 3. We had to go from 10 to 1 to 3. In other words, we had to convert it to an annual basis and then convert it to every 3 years. All right, we're coming down the home stretch, and this time I want to take in the information I have in my table of values and try to write an exponential function. And it was important that they said assume that the table of values represents an exponential function. Otherwise, we wouldn't know whether it was linear or exponential or something else in between. But the key is, we stressed in the very first slide in the opening minute that what we're doing here is we're taking this number, we're multiplying it by my growth factor to get this number. So the question becomes, what are you multiplying by, right? What did you multiply 1,250 by to get an answer of 1,725? So in other words, here's what we're going to do. In order to determine the growth factor, or better yet, we'll just jump right to the value of b. It's going to be 1,725 divided by 1,250, and I got, let's see, I think that's 1.38. Let me double check. Yeah, 1.38. So it's growing at about 38%. But that's not on an annual basis, that's every 5 years. So as far as putting the entire equation together, let's say f of t or a of t, whatever the notation might be, I'm just copying what was in the table there, starts off at 1,250 for an initial value, and it's increasing with a growth factor of 1.38 raised to the t divided by 5. And then of course we could convert that to an annual basis if we wanted to. I tell you what, I gotta confess, I've really enjoyed this particular topic and working on this video, and I hope you can appreciate the topic and its practicality in the real world. And I'll tell you what, researching this particular question, though, was a little bit sad because I love the city we live in, and I think it's the best place on the planet. But it's sad to see the population drop over the past few years. But anyway, we want to focus on filling in this third column, which is going to measure the rate of change, or in other words, it's going to measure the growth factor over a 10-year period. And so similar to what we tried to do in the last slide, what we're going to do is to try to figure out the rate of change over this 10-year interval between 1980 and 1990. We're going to take 328 117 and divide it by 357,870, and my rate of change is going to be 0.916861. Okay, and then I'm going to just continue that pattern here for the next couple of years. Let's see, I'm going to try to divide these two numbers right here, and when I divided those, I got 0.891901. So the population from 1990 to year 2000 dropped approximately 11% because in my head I was just subtracting this number from 1. And then last but not least, we'll divide these two numbers. And this time I got 0.892916. And so again, a population dropped another 11%. Now, interestingly enough, what they want me to do is they want me to find the average 10-year growth factor. So in other words, take the three answers we just got and average them together the same way that you might average your 3 test scores together. We're going to add them together and divide by 3. So again, here's what I'm doing. I'm taking this number, adding it to this number, adding it to this number, and then dividing by 3. And I ended up getting an average rate of change of 0.900559. So that's telling me on average every 10 years the population drops about 10%. And as far as writing the equation, well, I'm going to need the initial population, which we're going to say the very first number they gave me. I'm going to let that be my t equals 0, or the beginning. And so this 357,870 number is my initial value. 357,870. 357,870. Okay, now I've got 0.900559, and that's going to be raised not just to the t, but remember it was every 10 years because of the data that we had at our disposal in the table, so t divided by 10. And this is an equation that I think could be used to model the population of our city. And then you can make predictions. What's the population going to be in 2020 or 2030 based off of similar data? So anyway, nice job hanging in there tonight. Anything that was a little shady, we'll spend a little extra time practicing tomorrow. And don't forget, we got your back, and we'll get through it and figure it out. So have a great night. We'll catch you tomorrow.